Okay, so um, yes, it's interesting too when we try and look at the challenges we all face today with regarding our farms and our farming systems. There are a number of challenges around how we manage our farms and our cropping, both in terms of improving our health of our soils, managing our biodiversity on farm, and obviously the challenges we also face with improved water quality and managing our nutrients and inputs. Building climate resilience, there's obviously bigger challenges now around our weather patterns and the intensity of our rainfall patterns that we seem to be getting, particularly with periods of either wetter, hotter, cooler, warmer conditions are all adding challenges. And then obviously, last but by no means least, we all obviously need to recognise the importance of profitable farming systems. And that's one of the reasons why I did actually quite like this graphic that actually does recognise the profitability of our businesses. And obviously that does play a part in how we will then manage our farms for those other requirements as well. So essentially enhancing and improving our soil health is going to be important for managing our resilience in our farming systems in these challenging conditions. So there are various different sources of information, but I would say we are lacking really a very useful and comprehensive survey of cultivation approaches on farm. In the UK, there used to be a survey done by HDB, which obviously does help just to understand on the percentages of different systems used on farm. And by that, in a tillage environment, e.g. with mainly combinable and annual crops, we talk about conventional tillage, conservation tillage, and zero tillage. So conservation tillage, I also define as non-inversion tillage. Conventional tillage is multiple ploughing. So this is actually from some Euro statistics from 2016 that has a range of different countries there. You can see with the primary tillage classifications and their proportions. And we can see there at the bottom is the United Kingdom, where I think this is still fairly relevant to our current situations, where we've got just under 60% under conventional tillage. And then we have about 35% in conservation tillage and around 5% in zero or direct drilling. Obviously, there are very important both agronomic and climatic and management scenarios as to why we have our different cultivation systems. Obviously, soil type and cropping all will depend a bit on what systems we use. The important thing really is obviously to actually find a system that is suited to your soils and your cropping types, and obviously to have flexibility in those systems used with respect to our agronomic management. So, for example, where we have grass weeds, using multiple ploughing rotationally obviously is an important cultural control element of that. So I've defined ranges of tillage approaches, and you'll probably hear me say on numerous occasions that I am not a fan of the word minimum tillage, because I don't think it really actually defines a system very well. Minimum tillage can involve a very large high horsepower tractor pulling a very large tillage train, and there's nothing minimum about that. So I define tillage systems in terms of inversion tillage, which is using the multiple ploughing, which obviously is more energy intensive than some other of the systems, but has advantages in terms of managing weeds and producing seed beds under certain conditions. We then have non-inversion tillage, so that's not inverting the soil, but is generally mixing the soil. And then within that, I then classify that depending on the depth of disturbance as to what that's doing. So anything you can say, for example, a light, shallow cultivation, no less than 3 or 4 inches, or obviously something that's more disturbing 25 centimeters. So I just say it's non-inversion and then 20 centimeters disturbance. We then have what I define as single pass systems. So this is either single pass for establishment crops and can involve cultivation approaches such as strip tillage, where you're cultivating bands of soil that you then sow into, and you're not disturbing the entire field area. And then obviously you have the least disturbance type of system, which is direct drilling. And in my view, that should literally be just enough soil disturbance to open a slot, to put the seed in and close the slot, and no more than that. So as I mentioned, with those systems, you can then look at their intensity of the tillage, and moving from multiple ploughing on the left, we can then go through to the non-inversion systems, defining the depth of cultivation, to the single pass systems and strip tillage, and then obviously with the least intensity tilled type approaches, such as direct drilling on the right-hand side of the graphic. And that pretty much covers our main cultivation approaches in the UK. So why is tillage and tillage management important? Well, if we think about our soil and our soil management, soils are becoming increasingly vulnerable to damage, particularly after prolonged periods of wet weather. For example, the last 6 months we've had. And a lot of our modern machinery, whilst we've got huge advances in tyre configuration and tyre pressures, tyre management, which will help spread the loads over greater surface areas, the challenges are that over the last 50 odd 60 years, you can see the increase in weight of our machines. And that weight is transferred via axles and will obviously impact, depending on the soil conditions, on the actual soil, and potentially causing impact. And so this was just a graphic to show the soil stress at just under 0.5 meter depth over the last 60 odd years, having essentially a 14-fold increase with our weight of machinery. So that's something to bear in mind. There's obviously costs associated with our tillage approaches as well. And again, there's, as I mentioned earlier, there are agronomic factors that we do need to consider when we're choosing systems. But obviously, the more intensive cultivations that you have, the more costs associated with those. And you can see here, just as an example, a more conventional plough-based system, the establishment costs are circa about £200 a hectare. Moving to deep non-inversion, you can take off 60 odd pounds per hectare. And moving to direct drilling, obviously there's much fewer field operations, and so the actual use of both sort of labour and diesel associated with those costs can be reduced further. But as I say, there are other reasons, not just on those savings in fuel and labour, that we need to account for, and obviously rotational management, grass weed management, etc., are very important, and cultural control of those is becoming increasingly important. So just moving on to the main theme today from my presentation around the STAR project, is looking essentially at a long-term rotational trial that started in 2005 and was set up with 4 rotations. So that involved winter cropping, spring cropping, continuous wheat, and alternate fallow. The alternate fallow has now become a rotational herbal ley. But again, it's looking at how we can build resilience, soil fertility, improving soil structure within the rotation. And those then are crossed over with 4 establishment approaches. So that's annual ploughing, deep non-inversion tillage, about 20 centimetres soil disturbance. We have shallow non-inversion that's targeting about 10 centimeters, and a managed approach, which is based on conditions at the time of cultivations, and also our, if you like, our knowledge of the field in terms of grass, weeds, or crop residues. And that's essentially what most of us are doing on our farms today, is taking account of the conditions and choosing the most suitable approach. And then that's all crossed over in 3 replicates. So we have a large field trial, and hopefully the rotation as such. Essentially, the winter cropping is winter break with winter wheat. Spring cropping is spring breaks with winter wheat. Continuous wheat is as it says, continuous wheat. And then the alternate fallow / herbal lay, as I say, for the first 12 years or so, we had a fallow and a first wheat. And when it was a fallow, we had a mustard cover crop, because at the time when the project started, obviously things like the cover crops were fairly early in their use on farm, but we wanted something that was just providing cover, providing some roots to improve that sort of structure. And obviously wheat prices at the time, again, when this project started, were very low. So hence the sort of choice of fallowing and then having a first wheat to try and maximize the margins from that. Obviously times have changed, so we've tried to look at, once we've got a good data set from that first approach, we then said, okay, this isn't obviously giving us the margins that growers really would feel comfortable with. And we've therefore went for a rotation where we've included these herbal lays. So we've had first and second wheat crops, and then a period of herbal lay, as I say, to build soil structure, build soil fertility, manage grass weeds. The start site is a clay loam, so it's reasonably heavy, and does obviously have a certain amount of grass weeds on site that we have to carefully manage. And obviously that then becomes interesting in terms of when we're looking at our rotation and our cultivation approaches, how that impacts on grass weed burden. You will see in 2024, we were due to have a break crop here. We established oilseed rape. Obviously, there were challenges with all the conditions with the weather and the challenges, obviously, of flea beetle. So unfortunately, we weren't successful and that crop failed. So we re-established those with winter oats. We also sowed our winter wheat as a continuous wheat in early October. Conditions were good at the time. Established in terms of the seedbed was good. But following that, we obviously then had the challenging weather conditions, and that was a challenge. But I'll come on to that in a bit more detail on the following slides. So one of the real benefits of having a long-term study such as the STAR project is the measurements we can take across the treatments, looking at impacts from rotation and cultivation. So we were fortunate recently to have a PhD student, Joe Martlow, who looked at deep-seated compaction and was really interested to see what impact the rotations and cultivations had on the condition at depth of the soil. And he took many measurements both in field, such as penetration resistance and volumetric soil moisture, but also laboratory measurements using intact soil cores taken from the field to look at unsaturated hydraulic conductivity, organic matter, bulk density. And what I'll just spend a couple of minutes on this morning is also some image analysis using the X-ray CT scanning. And that was really interesting because that really can highlight the differences between our approaches used. So, for example, shallow continuous wheat, we can see there in the top left image, has a reasonable network of pores, but obviously a fair amount of, if you like, areas that are not linked through with pores. So the black areas are areas that are not containing pores within the soil. And you can see, compared to the shallow alternate cover crop, you can see the very difference in that image with the very high and much finer network of pores you can see within the shallow cultivation alternate cover crop. We then can compare that to a deep alternate cover crop, where again you can see quite a dramatic difference in the pore structure. Much, again, a reasonable level of larger pores, but a much lower network of fine pores. And then we have plough alternate as well, cover crop, where again, large pores, but much fewer finer pores that obviously do help with drawing moisture during high intensity soil rainfall events rather, and also for storing water as well. And again, with our conditions around climate change, these periods of either prolonged wet or prolonged dry weather is really important to try and improve our soil structure to allow it to absorb that moisture and to retain it as well. And that can be quite clearly seen with these images. In terms of soil strength, we can look at essentially a measure of how roots may become restricted with essentially increasing pressure that they have to exert to grow down through the soil profile. So we can take penetrometer measurements, which is essentially pushing a cone vertically through the soil profile and measuring its resistance. That resistance I've converted to a percentage that's what we call a relative soil strength as percentage of potential root restricting. So 1.5 megapascals is considered to be potentially root restricting, and that is what I've labelled here as 100%. So you can see there, as we go down through the soil profile, which is on the x-axis, sorry, the y-axis, we can see the changes there in the different cultivation approaches. So ploughing deep, generally having a looser, less resistant soil structure compared to the non-inversion, to the shallow non-inversion. And the shallow non-inversion there you can see has an increased strength that starts to deviate at about 10 centimeters and stays at about 25% increased strength all the way down the profile. That doesn't necessarily mean that we get impacts on crop performance, because it depends. Obviously, soil strength is very closely related to soil moisture. So as the soils dry and become harder, that's when the higher soil strengths for root growth obviously could impact on crop performance. Out of comparison, we have an analogous study on a lighter soil type up here in Norfolk at the Morley Research Centre, where we have a similar trial with the same analogous cultivation approaches, so plough, deep and shallow non-inversion. That's on a sandy loam soil compared to the clay loam at the Star Project in Suffolk, and you can see there that actually we do see similar trends in terms of the shallow non-inversion, both exerting higher soil strength compared to the deep and plough approaches. As I mentioned, although that higher soil strength can impact on crop performance, when we've actually looked at it, and this is looking at a period of the wheat crops across the STAR trial, we can see there that yields obviously vary from year to year, as you'd expect, but in very few years, you can see there where we get significant impacts on yield changes between cultivation approaches. So we can see there in year 2, we had a significant effect with the plough yielding the highest. And then again, in year 12, we had on yield, but again, actually that started to shift with the non-inversion approaches actually, and particularly the shallow non-inversion doing well. So we do get that seasonal effect year to year, but actually if we look at the yield compared to ploughing over that period of time, this is in winter wheat, we actually see the resilience from those cultivation approaches. So very little difference overall in performance. So if we say that the plough is 100% yield, our deep non-inversion is also giving 100% of the yield, and our shallow drops by 1%, just to 99%. So yeah, tillage is not having such an impact on our wheat performance in this period. However, when we do have these challenging seasons that we've all experienced very lately, that does clearly have an impact on our performance of the crops. And this was just an image we took in September at the site. As everyone can remember, we've had a really prolonged wet period of weather. Even at the best will in the world, the water volume of water is just too challenging to actually have that drained off the site. So we did, as you can see there, see areas of ponding in the field, and data from a local weather station that's part of the Cosmos data set. So I have to acknowledge Cosmos for their information, which is really valuable to looking at that what that means in terms of the weather. So you can see there in October, we had a very significant volume of rain. So that's probably getting on for 4 times the monthly rainfall for October. But you can see there right through November, December through to March, high levels of rainfall. And if you look at the volumetric water content, we were pretty much at field capacity over the whole period. And even in March, that was still very high. And that is really challenging when we're trying to manage our crops and trying to establish crops. So as I mentioned, we were looking at establishing break crops. So we had our continuous wheat, we had our winter oilseed rape that failed, and our winter oats that also failed due to the very wet conditions. We were planning to have spring cropping with sugar beet, but I'm sure a lot of you can appreciate the challenges around rotational and the longevity of a trial such as this, where we need to also consider the longer term impacts of our decision making on our studies. So we felt that although sugar beet obviously is really interesting, we would have liked to have had, the challenges are that in terms of our rotational progression, we want to go back into a herbal lay in the autumn, and the challenges of lifting sugar beet later, and then obviously not having a window or not having the optimum window for establishing the herbal lay would have then impacted on future seasons at the site. So we decided to take a year out from cropping, which will clearly have an impact on our margins, but it was felt that was the best for the longer term progression of the project. However, the wet weather did allow us to have an interesting consideration to say, okay, well, what impact does that really wet weather have on the structure of the soil under the different rotational and cultivation approaches at the site? So we went in May to look at the visual evaluation of soil structure. So that's the VES, which is a really nice technique that helps you to look at the structure of the soil. So you essentially cut out a block of soil using a spade and then look at its porosity, its structure of the aggregates, the porosity of that soil, the rooting of the soil. And you can see there that when we scored this, we looked at the continuous wheat rotation and the plough deep and shallow non-inversion. And you can see there, actually, the cultivation had very little effect on the VES scores. Surprisingly, and apologies, these images are a little bit small, but you can see, particularly in that upper left-hand image of the plough approach with the continuous wheat, that volume of rain we had did obviously cause some surface capping. And obviously, as that's dried out, we did actually observe a crust in the top sort of 2 centimeters of that layer, where obviously the sort of weight and volume of water have made the sort of aggregates and the soil particles run together and cause that cap. There wasn't actually significant impact at depth. All the soils were structured well. You can see there they've got good porosity at depth as well. what was most interesting was actually between the rotations. So comparing the continuous wheat to the herbal ley, there was a really clear benefit of having that herbal ley that's been in for 3 years, and then we've had 2 years of winter wheat as a first and second crop. But you can see there how the soil structure is vastly improved with much better aggregation. Again, on this soil type in these conditions, actually ploughing is obviously a really good way of keeping the porosity in the soil, maintaining drainage through the soil as well. You can see as we move to the non-inversion systems, and particularly the shallow non-inversion, because we're only moving the top sort of 5 centimeters or so of or 10 centimeters, sorry, of soil. We can see there that the natural structure of the soil is much tighter, as defined with our soil penetrometer measurements. So there is a good network of pores, but it is a much firmer, sort of more dense soil than you get with a cultivated soil. But it was interesting just to see those differences after the particular challenging conditions we've had. So just a couple of overall details of experiments or long-term experiments that are supported by the Morley Agricultural Foundation, both off-site, so we have sites in Suffolk and Norfolk that are looking at long-term farming systems. So we've got trials with cultivations and rotations. We're looking at soil amendments in a long-term trial. We've obviously got the rotational trial at the STAR project that I've talked about this morning. We have a soil nutrient trial, very long-term trial at Saxmundham that was actually established in 1899, and Niab have support us to deliver that, which is really interesting to look at the value of those on crop performance. And then we have the Morley Soil and Agronomic Monitoring Study, or SAMS for short, that is also a really interesting study. And there's much more information of these on our website. But just to say, these long-term studies obviously are really valuable in terms of what they can bring us. So this is an example of a long-term winter wheat fungicide performance trial we've had at Morley that started in 1986. And actually, when we look at the differences in terms of the timings of fungicides, so the sort of T1, T2, T3s, and from the mid-90s, we looked at T0 applications. Sorry, mid-2000s, we looked at T0 applications as well. And we can see there the value of responses varies obviously by season, but obviously considering our changes in climate patterns, actually having a really long-term data set allows us to look at changes across time and respective to the weather patterns that we get. So obviously going forward, where we might get milder, wetter winters, actually the value of our timings for fungicides may change, and we can monitor and record those responses. And as I mentioned, all this information is available. On the Niab website, we have a farming systems, agronomy and farming systems page with links to long-term research projects. And the Morley Agricultural Foundation also has a nice overview if any of you are interested in looking at these in more detail. As I say, there's reports that are available online. So thank you very much. That concludes my talk. So I'd be very happy to take questions. I'm just going to stop sharing my screen so that I can see if anyone wishes to ask a question. Please raise your hand. Okay, so Graham has just put his hand up. I'm assuming that hopefully there's only one Graham, but yeah, please go ahead.
Do you return any organic matter to the trials at the STAR project?
Yes, so all residues are incorporated after. We have looked at organic matters. We don't see, so far anyway, we haven't seen a huge shift under those cultivation or rotational approaches of organic. There's small changes, But obviously the measurements of organic matter, it's very, very, very hard to get that very fine granularity from organic matter measures. There are obviously, it's an important measure, but likewise, some of our other measurements, both for physical and chemical properties, are obviously valuable as well to pull that. So I'm sure a lot of you are aware of the HDB work that was funded looking at the soil health scorecard that was developed. So it's taking those three elements, the physical, chemical and biological, all as part of looking at your overall soil health. Yeah.
I was always thinking about returning straw or adding organic matter. That was the approach I was thinking of more than
Yes. So that's there's obviously at the STAR project was very much on the sort of rotational cultivation elements, and we incorporate all the residues. We have, as I mentioned, those other long-term studies where we're looking at soil amendments, or at Saxmundham where we've been applying farmyard manure long-term. We can actually see the value of those in terms of nutrient and fertility building, which, yes, are a really important part of our farming systems. So Lydia has got her hand up.
It was just a little bit in response to what Graham said, actually. Those of you that might not have seen the herbal ley growing, it produces an enormous amount of biomass. And I know we cut and took some of that away, but did we leave some of it on the site when we had the herbal ley in, Nathan?
Oh yes, that's a good point. In terms of the herbal ley, yes, we did bale and remove the majority of the material. But obviously when we had that the time for destruction, we sprayed it off and then left those residues to then be incorporated back into it. Is there any other questions that people would like to ask at the stage? Please feel free. If you go on, oh yes, Elizabeth, yes, please, Elizabeth Massey.
Hello, I was very interested at the result of the VEST scores versus the X-ray scores of the root pores at the very start, because we're aiming for good VEST scores. But is there a contrast there between what the VEST score is saying and actually the diversity of pores in the soil?
There is, absolutely. You know, the VEST score is a really, I call it a sort of very nice practical way of looking at soil structure. But obviously you don't pick up that very fine detail of pore networks and continuity that you do from the CT scanning. So yeah, if there's ever a technology that could be developed to make that CT scanning more accessible to growers, I think it would be really valuable for them to look at on farms, and under conditions to look at that much, if you like, higher granularity of detail in the pore networks. So if anyone has any other questions, please put your hands up. But otherwise, if you go on the Niab website, you can find me and my email address for being contacted. I've just had a question. I will share the QR codes again. We're going to take a break after the next speaker. I'll share the QR codes in that break for any of those who missed it at the beginning. So without further ado, I'll move to the next speaker.
Nathan, it might be easier if I run my own slides. So shall I try sharing?
Yeah, please do. I have got them as backup if you need. But yeah.
Let me see if that works. I'm not in my usual place. So let's just see if it works. Okay, you seeing that?
Yes. I'm going to presenter mode then.
Yep, just doing that now. Is that okay?
Perfect.
Excellent.
Yeah, over to you, Lydia.
Thank you very much. Thank you very much for that, Nathan. And I have to say, obviously Nathan and I are colleagues and we talk together a lot, but it's always brilliant to hear the fine detail of what a colleague is doing. So I'm going to talk about herbal leys. I should have been last, and sorry for jumping the queue, David, but I fear that I might run out of battery, so I thought it was best to go second. And actually, it does slot in very nicely to explain some of the fine detail of what Nathan was talking about as well. So I've been working on herbal leys for a few years now, and not only have we been doing some work at STAR, which has been fascinating, but also we did some work before that, and that was one of the reasons why we decided to go into a ley at the STAR site. So just a quick resume, really, and you've probably all seen this 100 times, but the sort of underlying principle for why I wanted to have a herbal ley within an arable system was to look at bringing back some of the soil health parameters. Sorry, I had a band across the middle of my slide. I've got rid of it now. The organic agriculture can embrace this, but I think there's lots of other ways of pulling organic matter back into a conventional system as well. And so we've been looking at organic inputs. We're looking at ways of reducing the tillage, as Nathan already talked about in some detail. We want to look at scalable interventions. So this is why we wanted to look at herbal leys within an arable system, actually as part of the rotation. And just to remember that there are all sorts of incentives that are coming, and already the US farmers are paid for carbon capture, and I suspect that we may well get that in the future. And if we have an undisturbed soil, we have all those sorts of things that Nathan talked about in some detail, including the last one, which I guess he covered in slightly less detail, which is the potential for waking up the microbial community and all of the things that go on in that space, the microbial mediated mineralization of organic material that takes it from sort of dead organic material back into something that's usable by the following crop, and the production of big, healthy fungal networks which help to hold those pores together. So Nathan's talking about large and smaller pores, but it's all very well making them, but you've got to hold them together. And the combinations of fungal hyphae and the polysaccharides and the other bits of sticky material that are produced by all those different microbes, providing that glue that holds those pores together and retains that aggregate stability. So if we don't think about these things, these are the sorts of demons that we come up with. We can get depleted diversity, biodiversity, as opposed to just crop limited diversity. We can have a diminution of the ecosystem services, all those things that enable crops to be produced. And I think a lot of people think, oh, ecosystem services, that's pollinators, isn't it? And yes, that is one of them. But I think all of those species in the soil microbial community, they also comprise those ecosystem services that we need to feed and look after in order to maintain soil health. We then potentially have degraded, eroded soil if it's not held together, and we have the potential for diffuse pollution. That is the running off of or running through those valuable, expensive nutrients that we meant to hold on to, and of course, greenhouse gases. And I'm going to talk to you a little bit in a minute about ways in which we can address the two of the main greenhouse gases. But I think depleted soil carbon content is sort of at the base of what I want to talk about today. And this is a shallow, quite fragile soil structure that we looked at in one of our cereals events. One that definitely needs to be looked after and maintained. This is a Liz Stockdale slide, and it's a really useful one. Thank you, Liz, for sharing this. Just to remind us that there are three components to a great healthy soil: the biological, the chemical, and the physical components. And lots of us spent a lot of time wondering what the chemical outcome is for what you're doing to your soil, and indeed the physical, but not so many people look at the biological. And that's the bit that I guess I concentrate on most. So I could probably spend the next hour and bore you all to death with all of those different species and their important components within that. But I'm just going to pull out one of them, which has been ill-considered for many years and tends to be impacted if we have a tillage system which is perhaps too rigorous, and machinery that is perhaps too heavy, all the sorts of things that Nathan talked about. So this is a lovely slide prepared by my colleague George Crane, and it's a cross-section through a root, a growing, healthy, happy root. We've purged all of the plant cell content. So what you see there stained blue is microbial cell content, and specifically this is a mycorrhizal fungus, and you can see all of those, the little fuzzy areas. I don't know if my mouse will work. These sort of little fuzzy areas, which are called the arbuscules, which are all about nutrient exchange between the plant host, the happy plant host, and the fungus. And here's another one, and this is a little bit later in the season, and these big round structures are the vesicles, which are fat storage. So this is a happy plant, but it's in association with a lot of fungal material. And this is enabling the plant to access all sorts of mineral nutrients far away from its root system, and those that might be in an inaccessible form. And George did a survey based on some of the work that was being done in the Great Soils Project, and he looked at what species were there in different situations. So this is a simple arbuscular mycorrhizal fungal community composition. Don't worry specifically about the species as such, but look at the differences. So this is, are you using a lot of fungicide or not? And you can see the diversity in this set in a fungal community where a mycorrhizal fungal community where few pathogenic fungicides are used. If we look at disturbance, we have a similar thing. So we've got no soil disturbance on the left. So this is a direct drill type of approach right through all those different strategies that Nathan told you about, through to heavy disturbance. Again, you can see this complex community here, but what you might say is, well, there's lots of mycorrhiza there in the other places. They just happen to be different. But what George went on to find is that these bad boys are probably not associated with positive mycorrhizal benefit. So they're taking, but they're not giving much back. So yes, you might find that you've got an association there, but you're not getting a positive benefit. You're not getting that protection from pathogens. You're not getting that uplift in the phosphate that's available to the host plant, and so on and so forth. So really nice study, and that was associated with some of these operations that we've been talking about. So introduction of leys into a arable or a livestock system. Originally, these were made for a livestock system, of course, they're for grazing, but we thought, let's put them into an arable system because a number of farmers had been looking at set aside using a very simple grass ley to put some structure and resources that the microbial community needs in order to grow and become slightly more complex and not just be comprised of those sort of weedy species. And we know that the soil degradation costs that you get if you don't look after your soil are expensive. So even though there is a cost associated with introducing these leys back in, there's lots of positive benefits as well. Now, herbal leys are not an absolutely new idea. And in fact, they had been used in the past. Here's a lovely paper that you can see, 1908, by Robert Elliott, and he introduced the Clifton Park system of farming. And his view was, you need to have 3 components to a really good ley that's good for the soil and it's good for your livestock. And that needs to be composed of grasses, legumes, and herbs. So this was the basis for the herbal ley that my colleagues at Cotswold Seeds put together for some work that we subsequently did under some BBSRC funding. There are a number of these herbal leys. Cotswold Seeds produced one of them, but there are a number of others that you can obtain from various different companies. This just happens to be the one that we used in this project. So in addition to having soil improvement qualities, I just wanted to actually flag up before we go on. I imagine that most of you on the call today are arable farmers, but should you be mixed or be considering reintroducing animals into your rotation, I just wanted to flag up that these also have very positive impacts for the foraging animals. And so even if you don't have your own foraging animals, you could sell these as a high premium quality product to those that do have, and that includes things like making the nitrogen better usable by the animal, by reducing gastrointestinal parasites and improving the use of their protein. But I'm going to dash on with the expectation that you are mostly arable. So this is an experiment that I ran for 4 years. It finished just over a year ago. And what we wanted to do was look at what is the actual outcome of taking out an arable field and what are the best ways of doing this. So we looked at grazing it versus mowing it. We looked at a herbal ley versus a single simple grass clover ley. And we looked at 2 years versus 3 years. And we did this in various places. So the site that you see on the left is at Duxford, just south of Cambridge. But we also did the same thing in a slightly different orientation at other sites. And you can see one on the right there at Great Dunmow, which was run by our colleague Jeremy Durant, not part of Niab. He's a farmer, but he embraced this idea and got involved. And there was also one at Loddington under the direction of Dr. Alistair Leake. So back to what we were doing, we put this into a herbal ley, and then we ploughed or we direct drilled. So we went for the two extremes of Nathan's different potential tillage, as close as we can get to zero tillage with the direct drill, and the maximum with a plough and harrow. So those are all the different combinations. There's a lot of data out of this, as you can imagine, so I'm going to rather race through it. But here are the Duxford 2021 yield data. So this is after the herbal ley. We've gone back into winter wheat, and you can see on the left you've got the direct drill, on the right you have the plough, and take a look at those lines running through. So the top sort of dotty green line, this is the arable control yield, but please note that this is at 50% of the nitrogen. So when we went back, we had no nitrogen or indeed any other inputs during the life of either the grass ley or the herbal ley. And then when we went back into wheat, we then only applied half the nitrogen. And then the UK average for that year was down there a little bit lower at just over 7.6 tonnes per hectare. So it was a good year, that first year, 21. The arable site gave us just under 10 tonnes per hectare. But look at the herbal ley. This is the orange line on the right-hand side. We had a yield that was absolutely as close, but with a very lower input. And the mown was just behind. And the grass clover ley was only just behind using the plough. We did have a yield penalty in the direct drill. We sort of expected this because we thought we're probably going to get a little bit of nutrient lockup. And we also had a little bit of volunteer weeds. We were a little bit too light touched in controlling those. I'll come back to that in a bit. And then when we went into the next year, so we have on the left here, we have 2 years, then wheat, then wheat. So this is second wheat, and this is the third year. So we've had a longer herbal ley, and we've gone back into wheat. And again, we're getting a really nice response. There's the arable control, again, very, very close to statistically indistinguishable from what we were getting from the arable control, still on 50%. So we've got 50% followed by 50% nitrogen input. And you can see in the ploughed, so the direct drill is doing very well, and it's doing better than the arable control. And in the ploughed, we're still getting a really nice bumper harvest. Again, we've got that nutrient lockup, even though we controlled the weeds, the volunteers, we call them weeds because we didn't want them in the following crop. There was a little bit of nutrient lockup, which would, we know, be released in the following year. So I can't take you through all of the data, but we've got very similar performance in our other sites. Slightly different things happened, different volunteers, and in a very heavy, very, very heavy clay soil, the farmer decided to go into beans, and then he went back into wheat, but he also was getting these nice results. We had a quick look at forage. I'm going to skip this actually because you're probably not interested in forage biomass, but I did say when in the question after Nathan's presentation that we'd had that huge biomass for the herbal ley. So look at that graph on the right and look at those blue columns compared to the green ones, the huge biomass that you get from these herbal ley compared to a grass ley. And Nathan talked about pore structure. So back to pore structure again. This is a lovely slide from Emily Coolidge, one of our colleagues in this project. She used this fairly simple system of digging a pit down into the different leys. So we've got herbal ley on the left, grass clover ley in the middle, arable on the right. And very simple, if you dug your, well, before you dug your pit, you pour the dye down through that system, give it a little while to penetrate, and then we can visualize the outcome. So where you see a white area in the bottom black and white images, this is an area where basically the water has not penetrated. And that means that, number one, you've got full penetrability in terms of water running into the soil as opposed to running off. So you've got the potential for more erosion. You've got large areas within that body of the soil which are not being used. So it's unlikely that if the water can't even penetrate, it's unlikely that roots are going to easily penetrate into those areas. And you can see from the herbal ley to the grass ley an improvement, and then going to the arable, some issues there with compacted, unpenetratable, is that even a word, areas within the soil profile. And here we have it visualized in a little bit more detail. This is from I forget which of my colleagues did this. I think this was our colleagues at Sheffield, and you can see changes in penetration resistance with depth and tillage. Quite a lot here. We've got green is the herbal ley direct drill, and the these are on the right hand side of each of those sets. So you can see the penetrability is reduced, and particularly at depth. So we've got, here's the surface, second one is 21 to 25 centimeters, and then 46 to 50, 61 to 65. So a real difference in those different treatments, with a real positive outcome from the grass ley and the herbal ley. Soil water aggregate stability. This is Lydia Smith. This is one of the Sheffield students. Soil bulk density. And again, don't want to spend too much time on these slides, but we've got the arable control, the 2-year ley, and then the 3-year ley. And you can see these bulk densities dropping down. And that's what we're looking for. Remember that 5 is bad, 1 is good. And so if you could pull that bulk density down, then we're going in the right direction. And the soil water aggregate stability, we've also got a very nice outcome from the direct drilled versus the ploughed. I'm going to skip that because I don't think any of you are probably livestock farmers, but I did mention that we had a little bit of a volunteer issue going back into the ley the first year. We were a little tiny bit light touch, and in the Duxford site, we had in particular sainfoin and chicory was coming back in the direct drilled area. So some of that yield penalty we got in the first year was due to that presence of quite a few sainfoin and chicory plants coming through. The back 2 set of the ploughed, and so there was very good control in the ploughed set. Again, partly explaining that difference in yield. Look at the scale here, by the way, before I go on to the next slide. So we're talking about somewhere between 20 and 25 plants. And that was in 2021. 2021 grass ley, we had a similar thing. We had a little bit of a volunteer presence in the direct drilled, in the direct drill set compared to the ploughed set. Again, up to sort of 20-25 volunteers of grass and a little bit of clover as well. And then this is the following year. So my colleagues, my agronomy expert colleagues, they said, okay, well, we're definitely not going to let that happen again. And this was the herbal ley on 22. So you can see the scale here. The worst we got was 2 in the direct drilled herbal mown treatment. So an order of magnitude difference. So we had very good control. Still a little bit of nutrient lockup. Interestingly, a very different outcome in the Loddington site. So I haven't talked all that much about the other sites, but we did this because clearly people are going to say, well, is that going to be the same at my site? The Loddington site, slightly different pH. And at Duxford, we were sitting on chalk. At Loddington, a little bit more acid, a little bit heavier. And they didn't have any legume volunteers. What they did have was some grass volunteers. So they had some Fesculolium and Lolium and some Dactylus coming back in the following. And they also had at that site a little bit of a black blast problem, which we never had at all at Duxford. But not huge. You can see that the numbers of flowering grass per metre squared, not huge, except a little bit coming back in the herbal grazed, which we clearly need to keep an eye on if we're using this system. So, flushed with success with the results of this herbal ley system and the potential for improvement in soil structure and pulling all that wonderful root material down into the lower soil horizons, we went back to the government and were given a really nice grant, which has been running now for just about a year. It's a 4-year grant. It's going to run from 23 to 27, as it says there. And we were looking at a number of different species that can be used to capture high amounts of carbon. So we're really concentrating now on how we can grab hold of as much carbon dioxide out of the air and then fix it either as crop, as increased soil organic carbon, as root material, or indeed as something that is made into something within the marketplace to replace those non-renewable, non-sustainable feedstocks. So we're looking at various different crops, which I'll go into in a second, and looking at things like value scale. And also looking at, as one of those, the herbal ley system. It's a big project with a lot of partners, and we have all sorts of trials and demonstrations at a number of different farms across the country. We are looking at soil carbon capture and soil health measurements. So we're looking at baselining, and we're looking at a range of different tillage situations, not quite as many as Nathan outlined in his talk, and databasing this material. So this is very much about collecting data for you and engaging with you, the farmer, in a range of different ways. We're looking at 4 different sets of crops. As I said, I'll just talk about those in a second, and going into the various value chains. So here are the 4 crop types. We have the annual fiber crops, especially hemp and flax. We're looking at rotational cover crops. Nathan mentioned that a little bit earlier. We're looking at perennial biomass crops, and finally the perennial food fields in forage, and very particularly in that with quite a high concentration of work in the complex leys, following on for that nice project that we were just talking about. I'm personally the project lead, but there's a lot of different partners in that group. And I'm just going to dash through those crops. I know this is about the star site, but you might want to find out more about this project. So we're looking at flax. This is a flax that's just being pulled in Scotland. And there's the final outcome. So this is for going non-food mainly outcomes. We're looking at hemp, industrial hemp, big robust plants with a very deep rooting system, again going into a range of many different outcomes. Here's the harvest from Eloise, one of our top varieties, and we are looking at what's going on above ground and below ground. So this is the beautiful root system of a hemp that is struggling through a very poor quality damaged soil here, but it's still managed to work its way through and open that soil back up again. We're also looking at miscanthus with a number of different products as well as being burnt, and willow, probably the other main interesting biomass crop of interest, again, not only going into power generation. And we're not just looking at non-food outcomes. So we've got the potential for seed from flax. We have the potential for seed from hemp. And then we have these beautiful complex leys that I've talked about. And here's a lovely picture from Pasture for Life, actually, just giving you a real feel for how incredible that biomass can be in these complex leys. But we're also looking at cover crops and the potential for how cover crops can be used, yes, as a soil improvement, but maybe actually blurring the lines between cover crops and herbal leys. Just a quick flag up of the fact that we are also looking at perennial wheatgrass. So it's not a triticum, but it's a perennial cereal. And there's my colleague Jasmine standing in the middle of the field there. You can see it's a big, full, deep-rooting crop, and here is the outcome at harvest. Got a little bit of a way to go before we can get the harvest up to wheat. So the cover crops that we are looking at could be many and varied, but what we, and I'm not going to go through this because this is not enough time, I think, but all sorts of benefits from cover crops. We wanted to have a look at, and I will just dash back to that. Remember that there are many, many benefits from cover crops, but we also know that there are disbenefits. We know that the potential for weed pull through and rotational conflicts and management issues. So we've come up with a whole range of new mixtures. We have a brassica-free cover crop mixture on the left there, which we're looking at, which includes buckwheat oats and a set of complementary legumes. We have a rather wacky one here, which is ribgrass, chicory, and phycelia, and a third one, which is a Nathan special, looking at blurring that line between cover crop, following crop. So this would be established, and then we'll, with a following wind, will sit underneath the crop and continue to give you some of those benefits, such as the free nitrogen fixation. So these are the mixtures that we're going to be using in our Centre for High Carbon Capture Cropping project. We're only a year in, but I was a little bit worried about this middle one, and we did find that that grew really well during the winter. We had quite a cold, wet winter at the site in Morley where we established that, and even in the short period of time that chicory was there, we saw that it was giving you those big, robust roots. So we will be continuing that over the length of the project. And the reason that we chose these are to look at the different rooting complexity and depth, one of the many things that we want to look at in cover crops. We wanted to maximize the management for the following crops. So with the issues particularly that we're encountering in the centre of the country with flea beetles, a lot of farmers are very unkeen to include brassicas within their cover crop choices. We wanted to maximise, however, the biomass that we had over winter and indeed the cost of it, and then blurring the boundaries between the crop and the following crop. So we also wanted to have a look at different herbal ley mixtures. The one that we used at the Star site and we will be putting in there in the coming year was the most complex one, and inevitably the most expensive one. So we wanted to have a look at different options within the herbal ley sort of sphere. Here are the mixtures that we've come up with. So the simple lolium and clover ley is basically the control, and it comprises of only ryegrass and clover. There are some different varieties within there, so that looks a little bit more complex at first sight than it actually is. Then we have a much simpler, but perhaps a little bit more cost-effective medium diversity ley, which comprised of just 3 species of grass, 2 clovers, and 2 herbs. Then we have the full herbal grazing ley. So this is the one that we've used at Star and in my work at Duxford that I showed you a moment ago. And then we have a rather odd one, a no grass mixture. Again, this is quite a low cost option, no grasses. So the green is the grass, but we have a couple of legumes and a couple of herbs. And we are trying these with a range of different we have replicated trials here in the east of England, just south of Cambridge, and we also have a second site in the Cotswolds, and we will be comparing the outcome and the soil impact of those different leys over the next, well, we've already been doing it for a year, but for the next 3 years, and we have these replicated, and we're going to be looking at all of these things that you see on the left. And here is a quick snapshot of our Hinxton. This is the site over here in the east. We have a replicated set of those leys, and we already are seeing differences in the way that they're impacting the soil. So watch this space. We've had lots of fun. This was at the Morley site where we had an incredibly cold, wet, rainy day. And you can see my colleagues there, some of them pretty much in disguise as they are togged up to deal with that very wet situation. Thanks ever so much for all of my funders, and please visit us on the www.carboncapturecropping.com site, where you can sign up and find out more about that project. Now, thank you very much for your coming to my presentation today. I'm going to hand back to Nathan to look after questions.
Thank you, Lydia, for that. Really interesting. It's nice to see, how we are developing these rotations around more diverse species. I think that's part of farming systems, is trying to improve our diversity of species, as well as components of the and longevity of the rotation as well. So if anyone's got any questions for Lydia, please raise your hand. So I have one for, Ellie Roberts has raised her hand, so please.
Hello, that's me, my alter ego of Ellie Roberts. I used to be an Ellie Sweetman, but we, as part of this project, we are trying to set up a bit of a herbal leys network as well to feed into that, and then hopefully carry on beyond the project end. So if anybody is interested in growing herbal leys that hasn't already, and also people that have got good experience of it, we'd be really keen to hear from you. So if you wouldn't mind emailing it, myself or a colleague here, and I'm sure they'll forward on, that'd be really good. Thank you.
Thanks for that, Ellie. Yes, and Ellie is, I'm sure lots of you will know her, but she's one of our forage experts, and so she has an important part to play within that project, as does Nathan, in fact. And we're building that hub of information. So we're looking to give information about, for example, growing herbal leys, how to grow some of those other crops if you've not come across them, such as biomass crops and fibre ones. So if you visit our site, there is quite a bit of information up there already, and you can download our newsletters, and then you can also you can sign up to get them, so you don't even need to come to the site. We will send you the next newsletter if you want to, if you go to and sign up on that page. And that will also mean that if there are any events such as the one that you're at today that you might want to go to, we'll send you information about those events, and they will, I think, almost always, by and large, be free events that you can come along to, and nearly all of them will have basis points associated with them.
Super. So anyone else got any questions they would like to ask Lydia before she disappears?
I shall not disappear, but I'm just fretting about my battery, which is holding up reasonably well at the moment. You were going to ask a question, Nathan.
Yeah, I was just something that's on my mind is we talked a bit touched on it, I think, regarding obviously these herbal leys and looking at the margin performance. So growers obviously and yeah, we always look at yields and yield performance, but obviously we are all businesses as well, and margin performance is becoming increasingly important. And I just wondered, wanted to make sure we are capturing that information, so we can do some margin analysis on that. And
yes, to an extent. I mean, capturing margin information from those comparison of the 4 different leys will certainly compare the cost and the establishment and whatnot of the different leys. In terms of the margin within the STAR site, I hope and believe that we will be working together to incorporate that into your full data set, Nathan. Yes, it's a tricky one. As much as possible is probably what I'm going to say, because the concentration is a lot about carbon capture. We're looking at a range of different ways in which farmers can benefit. And one of our project partners, I didn't mention this actually, and thank you for the opportunity, is Farm Carbon Toolkit. So Liz Bowles has already set up a facility for farmers to find out how they can identify the amount of farm carbon on their farm according to what their cropping type is, and that's going to be extended and improved over the course of the project, so farmers can look to see not only what the outcome is with respect to their crops, but also what's going on in a continuous and hopefully additive fashion with respect to that soil organic matter, soil carbon within their farming system. There is also an app which is being put together by our colleagues at EnviroCrop. So it's a separate project, but it was originally set up for biomass crops specifically, but it will be extended to some of the other crops again over the course of this project, so that farmers can see what the cropping outcome is in terms of financial return, as well as some of the other sort of foci that we have within the project.
Great, thank you. Okay, if everybody's made it back, then without further ado, we will continue to our final speaker, David Clarke.
Good, thank you, Nathan. Hopefully you can see my screen and hear me okay.
Yep, thank you.
Great, perfect. Yeah, so I'm David Clarke. I'm a farming systems specialist at Niab, based at Morley with Nathan, but I've also been doing a PhD with Cranfield University and BGS, funded by Centre, but also using a lot of the trials that we have here at Morley. And we've been looking at whether cropping system models, so crop models, can be used as on-farm management tools, particularly around nitrogen. The crop models have been used quite widely internationally and in the UK to look at quite broadacre things, looking at the impacts of climate change on wheat, regional impacts, but their use at a fine scale advising on-farm management is quite limited, as you'll see in a minute. So we've been trying to develop these tools to inform on-farm management. There you go. Yes, forgive me with this slide. I recently gave a talk in Florence in Italy, so I had to provide a bit of an overview of UK wheat for some of the international audience, but I'll refresh anyway, it might be useful. So obviously very high yielding, some of the highest yielding wheats in the world, currently have the world record of nearly 18 tonnes a hectare, but 16 tonnes a hectare possible quite widely in good years. With this high yield potential comes quite high nitrogen rates, average around about 186 kilos over the last 5 to 6 years. But some data from ADAS suggests that can vary quite widely at a field level, from anywhere from nothing up to sort of 350 kilograms of nitrogen, where we're really pushing those high yields. Unfortunately, we've still got some work to do on nitrogen use efficiency. Some early work sort of 25, 30 years ago suggested that our nitrogen use efficiency in wheat was around about 70, 75% on average. And those figures are still sort of bounded around today, suggesting as our yields have got higher, we've we've not made massive gains in improving that nitrogen use efficiency. And actually, with the variation that we have in weather, both spatially here across the UK, but also temporally, season to season and month to month, that variation in nitrogen use efficiency can be quite large, particularly when we overlay the variation in soil, you know, the broad sort of variation we have soil based on geology and physiological factors, but also within field, those two things can interact and we can have quite fine spatial variation. So, going backwards, and a significant proportion of these inefficiencies are a result of within field spatial variation. So we apply blanket rate nitrogen, whether that be 186 kilos or something else, to a whole field, and we have quite a large variation in how that nitrogen is used within the field. Currently, these are either ignored, so we just do a broad acre single rate across the whole field, or we use management tools such as nitrogen sensors, N sensors, satellite-based sensors, which, when used correctly and in the right place, can inform quite useful management decisions, but also have their inherent limitations that are often overlooked, which I'll highlight in a minute. Again, we're based at Morley here, so in the sort of heartland of UK wheat area, and a lot of the data that I'm going to talk about today has come from the trials that Morley support. Morley's a good example. We see the variation in nitrogen N optimum at Morley. This is across some nitrogen response trials, plot trials that we've had on the farm over the last 10 to 15 years. You can see bang on the average there, about 220 kilos of nitrogen. But within that average is a real quite broad range of optimum nitrogen rates, ranging from nearly 150 kilos up to nearly 300 kilos based on site, season, field. And actually how we manage that and on farm, you know, we play for the average. We don't take into account that within field variation and across field variation without sort of adjusting for things like organic matter. It's been widely documented that optimum nitrogen rate can vary quite broadly within a field. Some work by Daniel Kindred and ADAS have shown that in quite a number of fields, this can vary by over 100 kilograms of nitrogen a hectare. You can see a yield map from Morley in 2022 there in the bottom left-hand corner, and we can see quite large spatial variation in yield, ranging from nearly 12 tonnes a hectare down to nearly 7 tonnes a hectare. And we do have some technologies that can help us manage that. Variable rate technologies can apply nitrogen based on the canopy size or a calculated figure of canopy nitrogen. You can see from the same yield map, if we'd gone back into March and had a look at what a satellite-based sensor was recommending, it was suggesting that we could, by applying potentially a greater amount of nitrogen on those low biomass areas, we might be able to lift the yield potential. But it's well documented these fail to consider sort of crop soil interactions. And we can see here from a soil electroconductivity scan of the field that actually that variation in yield is probably driven by variation in soil texture and soil available water capacity. Therefore, nitrogen is not the limiting factor, and therefore applying more nitrogen may not necessarily get the response we would expect if nitrogen was the limiting factor. So it's been recognised for a while that process-based modelling might be able to help us overcome this. Models take into account both soil and crop interactions with weather, site, season, and be able to identify how we should appropriately manage these spatial variations, take into account season, soil, and what the weather is within that year. So how do these work? Well, I've been working with a model that has been developed by Rothamsted called the Sirius model. It's based on the Ceres wheat model that features in some of the big global models. In very short terms, we can supply the model with data on our management. So when we drilled the crop, how much nitrogen we applied and the dates we applied that. The soil, we can parameterize the soil based on available water capacity, permanent wilting point, soil depth, stone content, organic nitrogen content. We can supply the model with daily weather data, and then also parameters that describe the cultivars and the varieties that are specific to that region. So things like thermal time to specific growth stages. And then these models work on a daily time step and they can calculate biomass based on the weather conditions that we have and the resources available to the crop, both water and nitrogen. CHCx3 develops leaf area index for a sort of thermal time submodel on a daily basis, but it also can simulate the effects of water and nitrogen deficiency on leaf area index and therefore eventual yield. Just taken from the paper that describes CHCx3 there, you can see how that sort of calculations can be done. So effectively, when our moisture deficit exceeds 50% of the available water capacity for that specific soil, leaf area index is reduced, and actually when it reaches 83% of available water capacity, so whatever that 17% of our available water capacity, actually our leaf area index stops growing and we start to senesce. So it can then simulate these effects on yield, grain quality. It can simulate nitrogen and moist water movement through the soil, and gives us outputs that can inform management, both environmental optimum, but also economic optimum. So briefly, I'm just going to talk about 3 pieces of work. 2 of them are complete, 1 of them is ongoing. The first bit was we first wanted to see how these models are being used internationally. Are they being used at a field scale, and what are the limitations to them? We've then really wanted to test how serious is it capable of describing this very fine spatial variation in nitrogen use efficiency, and therefore can it inform quite fine level on-farm management decisions. And then we're at the process where we're trying to develop this method to be a more on-farm management tool that's more widely applicable. So in terms of how crop models are used, we are focusing right at the top of that tower at the subfield level to advise farmers on their management. We're not looking at global climate change studies or national governments. These are very much applied uses of crop models, and therefore the methods to parameterize them have to remain quite applied. So the first bit of work was a systematic review. Again, crop models aren't used widely for this currently. Only 71 studies internationally, that's across all crops, all continents, have been shown to use crop models to try and manage very fine spatial variability. One of the key limitations probably holding it back is the data we needed, certainly for the soil level parameterization. Every single soil type that we want to run the model on needs to be parameterized in quite detail. I'll see that in a second. And as you can see here, that as we start to move to scales of field level, so say greater than 10 hectares, or even a farm level greater than 100 hectares, the amount of sampling points used in these studies drastically reduces to sort of 0.1 sampling point a hectare. That's too fine or too coarse a resolution to really describe spatial variation of properties within field. So it becomes expensive to parameterize them. So we need better ways to capture that spatial variation within the models. And obviously in a UK context, we have very little evidence of it being used for UK wheat. However, there was promising signs that when they were parameterized in these quite high-level experimental studies, they then tended to perform quite well at describing the spatial variation. So actually, the models themselves may not need too much way in the further development. The challenge is actually just how we parameterize them on farm. So we've basically, in this study, taken an off-the-shelf model CHCx3 and seen how well it performs at a fine spatial scale. This has become even more topical. Earlier the year, DEFRA in this SFI have released a variable rate application of nutrient payment. This is £27 per hectare to support the variable rate application of nutrients. So actually, this sort of quite substantial payment could help to offset some of the costs needed to parameterize these models spatially if they could be shown to be working correctly. And that's the job we undertook next. So the easiest way to do this was to look at the high resolution data we have from some of our long-term experiments at Morley. We've been collecting data on some of these for over 20 years nearly at Morley. And you can see from the electrical conductivity scan across some nearby fields, we have quite big variation in underlying soil properties. And we can see that the new farming systems experiments there in blue is overlaid on top of some of this variation. We also have another long-term experiment, the straw incorporation experiment, which is a useful additional data set looking at nitrogen response in wheat over a number of years. The other advantage about these long-term experiments is they're not just looking at we just haven't just got that spatial variation underlying them. We also have different treatments. So although these were set up to look at different cultivations and rotations, on top of that, we have different nitrogen rates. So it's a really nice way of looking at how this underlying spatial variation interacts with these management, and how soil EC, which here we at Morley is basically a function of soil texture. We see the lower EC plots have a higher sand content, certainly at below 30 centimetres, and a lower clay content, but also stone content, raising to nearly 40% in those low EC plots. So we can see how those low available water capacity soils interact with different nitrogen rates. So bear with me on some, this is measured data, so this is not model data. This is what we've recorded across the plots over the last sort of 15 years. These are the 5 wheat years and then the mean on the average. So this is looking at the rotations data where we have the 3 nitrogen rates. So blue is farm standard at 220 kilos, green is half of that at 110, and the red is no nitrogen. And on the bottom of each graph is the soil or plot soil electrical conductivity, and on the y-axis in the top, which labeled A, is yield. If we go skip the individual years, but as you can see, generally across the 5 years, as our EC increases, all nitrogen rates, our yield has increased. So we have, on average, on these low EC plots, an average yield about 9 tonnes a hectare. On these high EC plots, up to 11 tonnes a hectare. And we see that same trend across all nitrogen rates. Interestingly, the second set of graphs is the grain protein, so grain nitrogen content, and we see that dilution effect. So we see the inverse, that although it's a bit noisier, generally the lower EC plots have a higher grain nitrogen content. And if we look at that 11% benchmark, which is an RB209 benchmark suggesting anything over 11% has been over-fertilized, it would suggest that 220 kilos on these low EC soils have a higher grain nitrogen above that threshold, and potentially we're applying too much nitrogen for the lower yield potential. And that has impacts on things like grain nitrogen use efficiency. So here, again, probably ignore the individual grey lines. They're the individual years, but the general trend is the red line that shows that on these low EC plots, our grain nitrogen recovery efficiency is below 50%. And we have about a 10% increase as we go up to that high EC soil, where potentially nitrogen rates are closer to where they need to be for economic N optimum. So the first question was, how well does a crop model, serious crop model, replicate that spatial variation that we see in the long-term experiment? So we can put the management information into the model. So when we drilled those specific crops, how much nitrogen had them, what dates they had it on. And we can also use the long-term weather data sets from Morley to input the model. And Sirius has been calibrated for a generic UK wheat cultivar, so we didn't do too much of that. We just wanted to kind of ignore the variety aspect of it and just get a typical UK wheat crop and see how well the Sirius performs. So the difficulty bit, as with all of this, is parameterizing the soil across that spatial variation. Sorry, that's the next bit, but I'll talk about it in a minute. But one thing we wanted to check was, one, how well does Sirius generally just model UK wheat crops without the spatial variation aspect in range of nitrogens? And that's where we turn to the straw incorporation experiment to see how the model performed. So just using data from the straw incorporation experiment, which has got 5 different nitrogen rates in wheat, ranging from 0 up to 250 across a number of years, we wanted to see how well the model replicated our recorded data on a typical soil that's representative of that straw incorporation experiment. We have the date of harvest, and obviously the model can give us simulated maturity, and it did a good job of modeling the different seasonal impacts of crop growth based on weather and certainly temperature. And you can see here that the model successfully recorded that longer growing season in 2015 than in 2014. Compared to the harvest dates there. So we had about sort of 2-week shorter season in 2014, and the model did a good job of simulating that. The error bars are basically the different nitrogen treatments. We obviously just recorded harvest on one day, whereas the model will give us a output for each nitrogen. We then wanted to see across those 2 years how well it replicated the full nitrogen rate spectrum. And we saw generally a very good response to yield, relative root mean square error of about 10% or 11%, about 0.8 tonnes a hectare in yield. So Sirius was able to model that response to nitrogen quite well. Not quite as good a performance when we looked at grain protein. You can see Sirius is overestimating grain protein a reasonable amount. This might be down to sort of cultivar parameters. The cultivar we used within Sirius is reasonably old now. We didn't do any updating of the grain protein concentrations or the variety-specific grain protein concentrations, or it could be other factors within the model. But we saw that when we combined the two to observe grain nitrogen offtake, those errors didn't accumulate, and we had generally a good simulation of grain nitrogen offtake across those different nitrogen rates. So that gave us confidence that Sirius might be able to be useful across the spatial variation on the new farming systems trials. So the first thing we need to do was, instead of doing every single plot, we just focused at the extremes of the variation we saw. So you can see here we've got the variation in sand and clay content across that electrical conductivity based on the plot data, but we've just parameterized the model for the two extremes. So we're going to call them a high EC soil, a heavy soil, and a low EC soil, our lighter soil with a higher stone content. And Sirius needs that, obviously, in some sort of mathematical quantification of the soil. You can see there the two different soils. So you can see that the low EC on the left there with a much higher stone content, much finer, sandier aggregates after breaking them down. And then the heavier, less stony soil on the right there was taken from those two plots. But Sirius needs that in some sort of mathematical representation. So we can provide it with things like the bulk density, the permanent wilting point, field capacity, total porosity, total organic nitrogen. So we see that actually because of that high stone content, the smaller volume of soil, although there wasn't too much difference in the total organic nitrogen in the topsoil, we did have slightly smaller pools of total organic nitrogen within those lower EC soils. And we can see a lower available water capacity, about reduced by nearly 1/3 on those low available water capacity soils, which goes on to explain those yield responses we saw earlier. So how well does Sirius model that response, observed response to that variation in soil? Reasonably well, with some caveats. So you can see there in some years, 2010, there's different nitrogen rates here. So the different nitrogen rates are by the squares are 220, the circles are 0, and the triangles are in between. And the low EC is the yellow, and the high EC is the browny soils. And generally that trend is the yield pattern that we see on those two different soils across those different nitrate is replicated really quite well in 2010, 2015, and 2020. And not quite so well in 2012. We had 2012 highlights the limitations of some of these crop models. We had a reasonably bad outbreak of septoria in 2012. Plot infection, global disease infection at a plot level was recorded between 15 and 18%. So Sirius overestimated yields because it isn't capable of modeling yield response to disease. So all modeling based recommendations need to be taken as a sort of best case scenario if we're managing everything else optimally. 2017, actually, we had some fescue problems on the trial, and again that across quite broadly across the trial, and that overestimation in yield in 2017 might be reflect that it's not simulating the impact of weed pressures. You can see that the grain protein isn't simulated particularly well. One of the main issues we identified within Sirius is that it kind of bottoms out, and it's about 1.5% grain nitrogen. This is within Sirius, it believes that crops don't ever fall below 1.5% nitrogen content. This was shown from our data to be out of date, and actually modern varieties where we have untreated yields, grain nitrogen content can be as low as 1%, even lower. So we've passed this on to Rothamsted. They have updated the model now with more up-to-date parameters based on modern cultivars. So actually grain nitrogen potentially could be simulated a bit better going forward. But again, we see good performance when we're looking at simulated grain nitrogen uptake. And the two differences between the soils, you can see that we observed about a 1.5 ton reduction in yield from our measured data and on that low EC soil compared to the high EC soil at 220 kilos. And Sirius simulated that response quite well. It simulated on average grain protein quite well, the differences between the two soils, although there was big variation year to year. And again, it showed that difference in nitrogen offtake, less than nearly 20 kilos less on those low EC soils observed and simulated. So once we have a model that we believe is describing the spatial variation in soil appropriately, we can actually use that to maybe infer some management decisions. Here we're doing quite a simple exercise by basically setting up within the model a nitrogen response experiment on each of these soils, and we could run that experiment over 30 years of weather data and see what the optimum nitrogen rate is on average across those soil types. And you can see actually there's not too much difference again, in a perfect scenario without any disease or weed pressure. Our optimum nitrogen is about 12 kilos less on the low EC soil. Potentially what's more interesting is actually in those years when potentially moisture is more of an issue, we actually see that 1 in 4 seasons, so greater than 30% of seasons, optimum nitrogen was below 200 kilos on that low EC soil, whereas on the high EC soil, that was actually only about 1 in 10 seasons. So if we are looking to reduce nitrogen rates, potentially on these lower yielding, lower sandy soils at Morley, that's where we should be doing it. There's also implications because we could model leaching, we could also model post-harvest soil nitrogen, and these soils, as we described, stonier, lighter soils, potentially higher leaching potential. Therefore, farmers could take that into account in deciding what management practice they want to include. So in summarizing that data, this is, quite a high level piece of work. We're not at the stage where we're applying it on farm, and I'll briefly talk about that in a second, where we're trying to develop these methods. But we've shown that Sirius, when parameterized with experimental data, was able to recreate spatial temporal variation across the long-term experiment pretty well. That actually with experimental modeling, this could be used to inform spatial variation on farm and potentially manage nitrogen more efficiently. We do want to go away and test different models. This was just one model, Sirius. We need to parameterize models for different cultivars across, there's hundreds of models available, and we want to see, do they all come up with the same conclusions? Is there variation between the models? And what does that mean for actually how confident we are in the modeling recommendations? But we also want to look at a rotational modeling approach. Obviously, wheat is just a small part of the rotation, and actually Morley will typically grow wheat, and then it will go into a cover crop followed by sugar beet. So if we could have a model that modeled both the cover crop and the sugar beet crop growth, we can track the environmental impact of a management strategy over the rotation. So for example, on those low EC soils, if we did have 220 kilos of nitrogen and we had still had a lower nitrogen use efficiency, where does that nitrogen end up? Are we losing it over the autumn in the cover crop, or is it taken up by the sugar beet? And therefore, how can we tailor our management practices to minimize the environmental risk associated with a specific soil? So very quickly, I'll just show you what we're up to at the moment. So the main issue with some of these models is certainly the models that have been used internationally that haven't been parameterized for UK wheat, we need to parameterize them based on how our modern elite varieties grow. So we're doing that using some of the data we've been collecting at Niab in some of our membership trials, where we've recorded quite detailed growth stage monitoring at Caythorpe, Morley and East Malling. You can see all the way across the season we're monitoring growth stages, or have been. And you can see here I've started to play with the model DSAT. This is probably the largest model that's used globally. And we can basically fit some key cultivar parameters to make the model accurately describe how crops grow across the UK. And you can see here that once we do that, so the circles are our measured data and the lines are our simulated growth stage with recorded weather data at Caythorpe, EMR and Morley. You can see the models accurately modeling that sort of delayed flowering at Caythorpe, the site further north, by about a week. So we can get really quite accurate growth stage modelling with these models that can then help us be used to inform nitrogen. We're also looking at some data sets from Rothamsted, looking at the Weegin data set to try and improve the other parameters within these crop models. So you can see here in the bottom right, they need things like parameters for kernel number per unit, canopy weight and anthesis, and area of first standard leaf. Well, we can use some quite high level fine resolution agronomic data from some of these trials to parameterize these for UK scenarios, so we can see how all these different models might perform and do they come up with the similar recommendations. And then finally, we're seeing how we can apply this across farms. So obviously I've shown how we can use these models perform on a long-term experiment, but really we want to know how they can be used on farm. So can we use things like our soil electroconductivity scans, some targeted soil samples based on yield map clustering data? These are from the Morley SAMS project. These are 4 sites within 2 fields at Morley. You can see the variation in EC on the left there. You can see how the long-term yield performance, so cluster 1 is a really high yielding cluster, cluster 4 is the lowest yielding cluster, and then our SAM sites overlaid with that. We can parameterize the model with the soil parameter, the soil measurements we've taken at each of those sites within those management zones, and we can see how well the model performs. So I've just plugged it into Sirius here and tried to recreate the 2019 season. You can see the yield map from 2019 is the final map there, and you can see that Sirius, as a standardized yield across the 2 fields, does a really good job of simulating the spatial variation across those 2 fields based on the SAMS data set. So we've got a good idea that the model is describing what the spatial variation, what's causing that spatial variation in yield, and therefore we might be able to use it to inform how we manage that spatial variation better. But there's a lot of work to do there, and that's where we're going next, and using the data that Morley collects and Niab's collecting to try and build a modelling platform that can help us further, not just nitrogen, but other things like sort of soil carbon and potentially phosphorus and things going forward. So I'd just like to thank you, obviously, some supervisors at Cranfield, for Stephen Hallett and Jack Hanan, obviously Elizabeth Stockdale from Niab, and Ben Marchman from BGS. And then obviously the Morley Agricultural Foundation supported pretty much all of that work that I've talked about today. And obviously David Jones has been farm manager there since I've been involved there, and for the last 10 years, more than that now, 12, 13 years, helping us manage those long-term experiments. And obviously Nathan and Jack, who manage those long-term trials and allow the data sets they collect to be used for the sort of extension research that we've described today. So I'll leave that there, Nathan, and got time for any questions.
Yeah, thanks, David. So would anyone like to ask a question to David? Well, I've got this opportunity. So Graham, please ask.
Is there any way we can, obviously a low soil electroconductivity numbers poor, is there any way we can actually increase it? Does cultivation or organic matter change that?
So soil electroconductivity is at Morley, before you actually sample what's causing it, can be caused by quite a number of different things. At Morley, we see it strongly influenced by texture and stone content. If we think about what else can influence it, so if you have quite compact soils that are where the particles are quite closer together, they obviously conduct electrical current better. So actually compaction can increase soil electrical conductivity. So we don't necessarily want to increase our electrical conductivity on those in that scenario, because that's caused by compaction, which is obviously going to have a negative impact. There is some work that shows that organic carbon, organic matter, will increase the water holding capacity of the soil. We are effectively, when we sample this EC, we are doing it at field capacity. So we're measuring differences in available water capacity, and that's driven by stone and sand content. So anything that might impact that, whether it's compaction, organic matter increases moisture holding capacity, whether it's even sort of low-lying areas which might sit a bit wetter, that might increase soil electrical conductivity. We also see data I haven't presented here. When we look at the farm level correlation between soil EC and texture and other properties, it works to a certain point, but we also see things like chalk content has an impact. Chalk can hold water, and therefore if you've got higher chalk content within the soil, it might give us a higher EC. So it's not a perfect linear relationship between EC and water holding capacity. Those relationships will need to be sort of established at a farm level, and higher EC may not necessarily mean a good thing for crop growth, particularly if it means that crops sit very wet or we've got compaction issues.
So also just to comment, because I'm annoying like that, I think it's important to recognise that here our EC is just it's a way of zoning. We're using it as a way of understanding the pattern of variation. It's not the thing really that's causing the differences. It's allowed us to spot that there are differences, link them to yield, and then investigate with a targeted sample what those factors are that are actually causing the differences. So then the question is probably not how can I change conductivity, but how might I act given I know what's causing the variation to manage my crop differently. And that's where the model might help us understand what the levers we might have on any particular site are to pull. So it's not we measured conductivity affects yield. It's like conductivity is one of those intermediate things that's giving us a clue that something's affecting yield. And we can then look in more detail, and David dug an awful lot of holes to understand what those factors were in the soils that were driving that difference, that was kind of highlighted by the differences in electrical conductivity, but wasn't just it.
To build on that, I think I probably had that final slide, probably had the maps in the wrong order. You probably start with your yield map and say, have I got sufficient variation yield that's consistent over a number of years that I need to worry about? And then you might ask the question, well, what's driving that? And that's where you might go to your EC map and say, well, it looks like there's something going on below the ground that's driving that spatial variation in EC, in yield that isn't sort of pigeon damage or weed damage. And then you'll go out and maybe dig 3 or 4 holes across that variation in EC to see actually what's likely driving that variation in EC and therefore yield. So it's kind of just a proxy for confirming that your variation in yield is driven by something below ground. And I haven't included here, we actually have EC scans at the STAR project that Nathan has managed, and actually we don't see any way near the same sort of relationship on that heavy soil. That EC doesn't really explain our plot yield variation very well, because that we haven't got those same limitations on water availability on those slightly heavier soils.
This seems such a complex subject. I was wondering if anyone had thought about, is anyone using machine learning, AI, to try and make their way through this complex?
So again, I haven't included it here. There's another piece of work I've done is looking at yield map data. So we had a large yield map data set from Morley and also from AHDB Strategic Farm East. And we used machine learning there to identify patterns within the yield map data set to identify temporally stable zones within the farm. So we know that over 10 years, that zone in yield performance is stable. Therefore, we can expect that within that zone, that whatever's driving that variation is consistent. So there's sort of homogeneous yield zones. And that was done with a clustering algorithm, machine learning clustering algorithm that tries to sort that data into patterns. And that clustering data that you saw on the last slide, that was done using that machine learning clustering algorithm to identify those zones within the yield map data set that we can then maybe go and sample without having to do those big grid sampling techniques that some of the studies in my systematic review had done. So yes, we're working on it. And actually a lot of that parameterization of the cultivars is done with some machine learning. So we basically tell the model to find the best parameters that describe the variation in crop growth and yield. So that those techniques are very useful and are helping us develop those going forward. But we do need to, there's people within Niab and outside of Niab that probably can do a lot better than I, and that we probably do need to talk to.
Thank you very much.
Okay, has anyone got any other questions for David? If not, I will just like to thank you all for attending today, and I hope you found it interesting. And as David mentioned, but I would like to reiterate, I would very much like to thank the trusts for supporting. So that's the Morley Agricultural Foundation, the JC Mann Trust, the Felix Thornley Cobbold Trust, and also historically the Chadacre Agricultural Trust, that have all supported the long-term trial work at Morley, and also in and around East Anglia. Because obviously, as you can see, the value of the trials, not only does it allow us to understand some of those interactions on an agronomic, cultivation, tillage, rotational effect, but as you can see from David's work, it allows us to look at models and how we can hopefully improve our management techniques in order to understand some of those approaches for sustaining our cropping systems in the light of changing climate and other drivers, policy drivers as well. So I would, as I say, lastly like to thank TMAF for supporting the Morley Lots initiative, which is the STAR project and other long-term work that's been supported by TMAF. And as it allows us to help to deliver such events such as these seminars and open events, and also material in terms of reports that are available on the website. So I'd like to again thank you all for your time this morning, and wish you a good day.